Hi, my name is Jose Pinilla. I'm a PhD candidate at the University of British Columbia, and what I'll be presenting to you is work in progress of my thesis related to the use of D-Wave machines. I've titled this presentation, The Impact of Embedding on Quantum Annealing Sampling, and I'll be presenting it with what I call computer-aided design or CAD perspective, which is in relation to my research group's background on CAD tool development for digital design. I think this subtitle describes very well our approach, but it also highlights how much progress there's been in the development and use of D-Wave quantum annealing machines. So let me first tell you what I mean by this CAD for quantum annealing. When you design a system, whether that's software or hardware, or when you come up with an algorithm or application for a quantum device, CAD tools are there to help you make the best use of resources and get the best performance in the process. This becomes very critical when the scale of the application makes the task of using the device itself a very hard problem. So CAD tools for quantum annealing are present in what I've built here, these 5 steps. So first, there's problem modeling, where you have to transform your problem that is solved by minimizing the energy of a Ising spin graph model, or a QO, spin represented here by S, but you can change that into, or I use interchangeably X to represent a QO. Then after this, you have to do graph embedding, where because of the limited connectivity between qubits, you require to perform a mapping of the problem graph onto those qubits, and then you end up creating qubit chains. Then the third part is parameter setting, where you have to convert those Ising model fields in the nodes and interactions between nodes into biases and couplers between qubits in the device. And of course, you have to stay within the range physically available in the device. The fourth you have to do is anneal scheduling, where you specify the time and curve of the anneal such that the conditions evolve from a superposition to the energy landscape of the Ising model. And then here you have to consider noise and other limitations of the device, which is why you end up collecting thousands of samples, and then you resolve the qubit chains to match the original problem. And this last step is what is called sample resolution. So you get those individual values of problem nodes resolved from those qubit chains. Now, there's been a lot of work on the different aspects of cash flow for quantum annealing. In fact, I only list very few of them here, only the ones that relate most to the work I'm doing. So it's important, I think, just to point out the scope of the work we're doing. The problem we're modeling is sampling for machine learning applications. We're interested in both heuristics and systematic embedding methods. We believe that parameter setting requires the use of extended range for better performance, and this is supported by the D-Wave tools. We are also interested in post anneals, having post in the anneals. We've had enough evidence showing that this is beneficial. We've witnessed a small opportunity of improvement in the sample resolution part using chain fractions, and I'll explain this a little later. So all of this is to say that CAD for quantum annealing still has a lot of research opportunities in all these steps. Right now, we believe that a comprehensive approach is necessary just to extract a better performance from the D-Wave machines. This makes sense for a new technology such as this one. It just means that there's so many research opportunities open, and that users should be aware of all these steps. So on that note, like I said, we're interested in the impact of embedding on quantum annealing sampling. And the way I want to introduce this is by first going through the reason why we look at these specific parts of the cash flow. Then I'll focus on how we can measure changes in performance, and then I'll go through some of the small experiments we've looked at. So why quantum annealing sampling? Well, maybe some of you watching already know the answer to this, but D-Wave machines first work as optimizers, providing us with samples from which we pick the lowest energy solution, or they can operate as samplers, since D-Wave machine can sample from a distribution close to Boltzmann. The reason we're interested in using the D-Wave machine as a sampler is because of its application to quantum-assisted machine learning applications. And just take a moment here to separate the idea of quantum machine learning from quantum-assisted machine learning, so QML against QAML, making the distinction that QAML works on classical data sets, meaning the device is used as an accelerator of an overall classical algorithm. And then the other distinction here that I'd like to make is between optimization-based QAML and sampling-based QAML. So some QAML algorithms exist, such as boosting, where the training algorithm can be modeled as a binary optimization problem. But we're more interested in those that are where the samples of the quantum annealer are used to characterize the model's probability distribution. However, we don't completely ignore the other applications. A lot of our work applies for both. Now, the golden example of sampling-based QAML starts with Boltzmann machines. We can use these probabilistic generative graphical models to model training data. Well, as long as we can set the parameters on nodes and edges of the model to maximize the likelihood between the model's distribution and the data distribution. Well, this, however, turns into a really hard task because exactly calculating the model's distribution at any point during training means calculating the partition function term that I highlight here. You have to try every single configuration, which becomes intractable with the problem with the size of the problem. Now, of course, that doesn't mean we can't train them classically. It just means that we have to limit ourselves to certain topologies and use Monte Carlo methods to sample. Well, first from the conditional distribution, which you can sample exactly. Then we use Monte Carlo methods to sample approximately from the joint distribution, which allows us to get our gradient and just do our gradient descent here in the training algorithm. Well, it's at that point where you can introduce quantum annealing sampling to replace the sampling step. This is the basic idea, and there have been multiple publications and there have been multiple application examples working on taking this further. So now that we defined our application, why do we look at embedding for this type of application? So as a very quick review, the minor-embedding problem comes up when we need to map our problem graph into the device's graph, whichever generation that is, whichever architecture. We'll need to do this if our model doesn't map one-to-one from nodes to qubits. It's very unlikely that it does. And now the problem here is not only that bad embeddings, in the sense that we use multiple qubits per node, will limit the size of the problem that we can embed. But just as important is that bad embeddings affect the results that we get. This is because first it creates the problem of having broken chains, so qubits assigned to the same problem node. When you sample them, they don't match. You have to resolve this somehow. But also because it increases the resolution necessary to represent each weight. And this is harder to tackle from an algorithm perspective, but it's good to have in mind. Now, working with embedded problems then also means that we have to bring in the last step in the CAD flow, which is the sample resolution. So to resolve those values that D-Wave provides for different to resolve the qubits matching to one node, we can use what are called chain break methods. So simple approach is you could just discard samples when there's a chain break, but then you may be left with very few samples, as the probability of having broken chains increases exponentially, actually, with the size of the chain. So you could go with majority vote, which is default mode. Select the majority. If there's a tie, you could either discard it or do it at random. Or you could do it completely random on the values that you get from the qubits. Just pick a random qubit from the chain and use that value. We have a very small contribution here, which is tied directly to our QAML application, and is that we can actually use the fraction itself as a result value. This is possible because we end up using those single spin values to calculate expectation values. So we don't need to actually resolve it. We can just keep that information of the chain fraction. And I'll show you some results later. Very small contribution, but I think it's important. Well, so the reason why we look at this embedding problem is that we expect that minor embedding will remain as a problem, and that algorithms we develop in this area will be just as important, in my background, as place and route algorithms for VLSI and FPGA. We especially see a huge similarity here to FPGA design in that even though we can build fully connected designs, there will always be an argument for lower connectivity at lower cost and most likely better performance. So this is for problems that don't need fully connected graphs. Of course, as we can create efficient mapping algorithms. So in the next part, I'll be talking about figure of merit. And by this, I mean, how do we quantify performance of our sampler, of our D-Wave sampler. And so this is actually pretty easy for optimization problems. If you're measuring the quality of the machine, you can do that with synthetic problems, where you know the ground state. So you find the probability of finding that ground state in your samples, or you can calculate a time to solution for the time it takes to obtain, or the number of samples it takes to get a percentage of your samples to be in the ground state or lower to some value. But if you don't know the solution, then you can look at simple statistics. You could look at the minimum or the lowest energy sample. The mean, this is a little problematic because the distribution of samples could have a very long tail, which means your mean just moves towards that. So it may be better to use median, which is what we used in our previous work on layout-aware embedding algorithms. You could use some mixture of this, where there's been some work on, for example, the pi-elite metric, where you do the average, but only of a certain number of elite samples, and that way you remove that tail. Well, but what do you do with sampling problems? So something where you could do is, if you know the full probability function of your distribution, then you could calculate a divergence, where you just compare probability of every configuration. Well, that requires knowledge of the probability of every configuration, and like I said, then you need to calculate this term, the partition function, where it just becomes very expensive. You could do this for small problems, that's okay. But if you have bigger problems, there's a trick that you could do, and I've seen this in multiple papers. You can do Boltzmann fit, where you could know the energy levels and the degeneracy of each of those energy levels, and then you can compute this for larger problems, because you only have to plot this ratio, the log of this ratio, and according to the energy, and then you can do a linear fit of that function. So it's very interesting. It's a good trick, and we've used this in our experiments. So now I move on to some of the experiments that we've done. So this is what I call embedding transformations, and what we've done here to test the impact of embedding is to create from a problem that matches directly into the chimera graph, we transform it to create different embeddings, like the name says. So if we have first a chimera graph, which has some disabled qubits, what we do is we can move a chimera-shaped problem, synthetic problem, and find a fit. So that's what we call a fit. And just find somewhere where all the qubits are available and all the couplers are available. We can then rotate that embedding to just assign nodes to different qubits. This would also allow us to measure variation between qubits. But we can then spread multiple times these embeddings. So it's just like I show here in this image, that would have more qubits because we create this chains where we didn't have them before. And so what happens if we measure Boltzmann fit for these different problems? Fit, rotate to different spreads. Because we're doing this for synthetic problems for which we know all the solutions. Well, fit and rotated, they perform very well. We sample from the lowest energy, we see here on the x-axis, and the dotted line is the global minimum. But then we see that when we have those spread out embeddings, well, we start getting gaps here in the samples. This creates an issue for the metric in that, well, we can't really do a linear fit of this part here. We'll have an infinite error for the match. It's still visibly identifiable that samples are not as good because it's shifted, but we're still left with the need for something better as a metric for this. And that's where we are kind of starting to introduce a more informed or more context-aware metric, and we're starting to use expectation error. So this is because, well, Boltzmann fit, like I said, requires knowledge of all the energies and degeneracies. Hard to measure with fewer samples because then you have more of those gaps. And then this brings back the idea of the chain fractions. We can't do Boltzmann fit with chain fractions. We have to actually resolve values because we need to get a discrete energy value in that range. So instead, we could do expectation error, where we calculate the expectation value for the linear terms for each spin, the expectation value for the quadratic terms, and then we compare our embedding transformation to the base or fit embedding that we had at the beginning. So this we can calculate, we can get that value for every single linear term and for every single quadratic term. This means we can perform that experiment and get what I'm showing here, where on the x-axis now we have the different embeddings. So we'll have a rotated, which should have our baseline. What if we only change the qubits assigned? We don't increase the changes. Then we have the first spread and second spread with different chain break methods. So if we use the majority vote, which is the default, but of course, if you're using this for sampling applications, you should not use this because there's a bias on the distribution, and we can see it here where it moves the median, the line, and it also moves the average very far. But if we use weighted random, we actually recover some of the performance, and then having an embedding is actually not a huge impact. And we see this among these 3 examples that we have here. So, well, if you're doing sampling applications, don't use majority vote. Simple takeaway here. We see that for the linear terms, and we also see that for the quadratic terms. So it's a little worse in terms of the embeddings, but we still have the same idea. The majority vote shifts away the mean, so you get a bigger error. And we can quantify this. So if we just do the Euclidean distance from all those points, we can get a number that tells us how far we are. And we just show here the same thing that we're seeing in the graphs. So as a summary, a comprehensive CAD approach is necessary at the moment to obtain measurably better results from the DWave's quantum annealer. So users need to be aware of configurations available, but not only that, suitable for the type of application. We still need device-specific figure of merits and application-specific metrics that should allow advancements in the CAD flow. As an example, we just show the difference between performance when we change a very small part of the CAD configuration for Boltzmann sampling of embedding problems. Finally, I'd just like to talk about embera, our Embedding Resources and Algorithms open source repo, where we treat this as a test bed of ideas that we'd like to contribute to D-Wave eventually. So thank you very much for watching my talk.